Okay, and again, for a finite volume, what we are solving is the time derivative of the integral over each control volume. Let's call it, if we are dealing with triangles, let's just call it Ti for the triangle I. Okay, of any conserved quantity integrated over a triangle would be added to the summation of each interface, right? Let me call it ij, right? Then j is in the neighbor of I. Okay, so basically I'm gonna be using j. So let's do a different mesh. So let's call it this is triangle 1, triangle 2, triangle 3, triangle 4. Then, for example, for triangle 1, the interfaces include, for example, I1, I2, I3, right? So it has these 3 neighboring interfaces. So I'm going to be integrating over all the adjacent interfaces of the triangle, and then this is the flux. Flux at x dot with the normal, okay, at x integrated with ds x. So here we are going to be approximating this entire thing as a single number. So this is going to be approximated as f of j, right? I mean, this is the approximation we have to make in finite volume. If you want a higher order scheme, you need a higher order approximation for this surface integral. You may have to start using, for example, a Gauss quadrature, as we learned in finite element, but this now applied to an interface, right? And you also have to use higher order finite difference approximations for the flux value at the points. But if you want just the second order, for example, finite volume scheme, what's the best, what's the Gauss quadrature formula to get you second order accuracy? How many points in Gauss quadrature do you need for second order accuracy? So yeah, 2n-1 is to give you a exact answer for polynomial of order n. And if you want an integral to be second order accurate, what's the order of polynomial do you need to integrate exactly? Second order polynomial? Well, we can take a small detour and try to figure that out, right? So if you have a function, let's imagine we just have a one-dimensional function, f as a function of x, okay? And we are integrating over now a small domain, right? So we are trying to integrate, let's say, from 0 to delta x. And we're trying to figure out how accurate how many points do I need for this integral to be second order? Okay, so we are trying to perform the integration. So we are trying to say what's the integral of fx dx from 0 to delta x. Okay, so we want to approximate it as a so let's say we want to approximate it as a Gauss quadrature scheme, right? So we want to write it as summation of I equal to 1 to n of wi times fxi. Okay? So the polynomial approximation of fx determines what's the order of accuracy, right? So for example, if you use a single point, so if n is equal to 1, then this Gauss quadrature is going to be exactly equal to the integral from 0 to delta x of the best linear approximation to this f of x, right? So let me just write f linear approximation to x dx. So now let's start to figure out what's the best linear approximation to f of x. Okay, so to figure that out, we don't actually have to find the best linear approximation, because we know that we just want to find a linear approximation that would actually work, right? So for example, the Gauss quadrature scheme would choose just the center value, f at half of delta x. And so what if we just say that we just use the linear approximation of the Taylor series? What if I choose f tilde x to be just equal to f of half of delta x plus f prime at half of delta x times x minus half of delta x? So the question is, what's the approximation power of this linear approximation? What's the accuracy of this linear approximation if I use 1 point? Any suggestions? What's the difference between this original function and this linear approximation? Or if I add a plus O delta x, what's the power of this delta x? It's going to be square, right? Because the next term is a square term. Okay, so this tells us that if we want a second order approximation to a function locally, right, we just need a linear approximation. And that means in order for us to approximate an integral over a small domain, we need how many points in the Gauss quadrature? Well, let's. Yes, if we want a second order approximation for the integral, how many points do we need in the Gauss quadrature scheme? Only 1 point, right? Right? I mean, this is because, well, the 1 point Gauss quadrature is going to integrate exactly a linear function, which is actually a second order approximation for the original function, right? In other words, the difference between the original integral and the Gauss quadrature scheme is exactly equal to the difference between the original integral and the integral of this second order approximation of the original function. Okay, so that's why you only need a single point to achieve second order in finite volume. This makes a second order finite volume scheme even in arbitrary multi-dimensions, 2-dimensional, 3 dimensions, exactly the same as a 1-dimensional finite volume scheme. Each flux, although being an integral, can be approximated by the value of the flux at a single point. Usually we choose that single point just as the center of the area or the center of the edge. So in order to evaluate the flux integrated over this edge, we only need to approximate the flux at the center of that edge. Okay, if you want higher order, the story is different. For example, if you want third order, you immediately have to have at least 2 points for the Gauss quadrature, and which also means actually 3 points if you go to 3 dimensions, right? The Gauss quadrature scheme to integrate over a triangle, for if you want it to be more accurate, if you want to be exact for anything more than a linear function, you have to have 3 points. Okay. So, but like for our second order scheme, we just need to approximate, which is an approximation for the flux function evaluated at the center of an interface. Right. Okay, now we can use exactly the same thing as we did before. If we, for example, just stick to a first order scheme, which we're going to implement, we are going to be using a piecewise constant approximation on both sides of the interface, and use a good enough scheme or our approximate Riemann solver for the interface flux based on the value of the solution on the 2 sides of the interface. Or if we actually want a second order scheme, we use a finite difference scheme to compute the derivative in every cell. And here only a first order finite difference is going to do. Normally the typical finite difference we use are either actually based on the finite volume itself. I mean, you can use finite volume to actually figure out the derivative of figure out the average derivative of a function within the cell, or you can use a least squares type of finite difference to figure that out, and then you perform the extrapolation to the interface and again use a Riemann solver or approximate Riemann solver to compute the flux.